My name is Jamila Green, and this is my Neuron story. I realized that the concept of physiology in the neuron story can be a tad bit complex. So for my neuron story, if you could just go along with my theme and just compare the neuron story and the whole synaptic transmission to an Amtrak train. An Amtrak train that makes numerous stops, similar to the nodes, has many passengers, lets people on, lets people off, which is similar to the transfer of ions. You know, when people get on and off, it changes the mood of the train, which is similar to the different charges and how the charges change. And then eventually, as the train continues to travel, it gets to its destination and everyone goes to where they belong, similar to when the neurotransmitters exit the terminal buttons. For my neuron story, you should just be familiar with a few key terms that I'm going to explain for you right now. Synaptic transmission is a process by which signaling molecules called neurotransmitters are released by a neuron and bind to and activate the receptors of another neuron. A neuron is a transmitting nerve impulse, and it's a nerve cell. A presynaptic membrane is a cell membrane of an axon terminal that faces a receiving cell, and a postsynaptic membrane is the section of a cell membrane of a postsynaptic neuron that is adjacent to the synaptic cleft. The postsynaptic membrane contains synaptic receptors. So here is the presynaptic membrane, the postsynaptic membrane, the neurotransmitter molecules, and the synaptic vesicles. This is all going on in that space, which is the synapse. So an event occurs, and there are four things that can happen. However, we're just going to focus on a few. However, one of the things that can happen is that the neurotransmitter molecule can be taken back up into the cell. The neurotransmitter molecule can dissipate and float away. The neurotransmitter molecule can metabolize, or the neurotransmitter molecule, can bind to the binding site, which is in the ionic receptors located on the dendrites of cell B. And that's exactly what we're going to focus on. Now, please keep in mind that the cytoplasm and the interstitial fluid are very significant because they contain ions. And these fluids are both inside and outside. These fluids, because of the ions that they contain, and these fluids are both inside and outside of the ion. There is a difference in concentration of 3 key ions in the cytoplasm and also the interstitial fluid. We determine this by using the oscilloscope, which we will discuss later. This area right here is the cytoplasm, and it's right here between the axon and the branches. This illustration shows the synaptic vesicles right here emptying into the synapse, which is right here, this gap, and then binding into the binding sites, which are the receptors, in the postsynaptic membrane. Outside the cell, it is equal. It has equilibrium and also interstitial fluid. And outside the cell, it has cytoplasm. The postsynaptic membrane is made up of a lipid bilayer. The receptors on the lipid bilayer are closed until the neurotransmitters bind. When binded, the sodium comes into the cell because of osmosis and electrical pressure, and the sodium is positive, and inside the cell is negative. Now, please, these are a few things to remember. Opposite charges attract, and same charges repel. Also remember that most cells all they want to do is maintain homeostasis. So the key for this whole neuron story is to maintain homeostasis. For this next section of my story, you should be familiar with the terms in green. An oscilloscope. For the next part of my story, one should be familiar with the terms in green. An oscilloscope is a device for viewing oscillations as an electrical voltage or current by a display on a screen or a cathode ray tube. Osmosis is a process by which molecules of a solvent tend to pass through a semi-permeable membrane for a less concentrated solution into a more concentrated one, thus equalizing the concentrations on each side of the membrane. Action potential is the change in electrical potential associated with the passage of an impulse along the membrane of a muscle, nerve, or nerve cell. An EPSP stands for excitatory postsynaptic potential. It is a postsynaptic potential that makes the neuron more likely to fire an action potential. And lastly, the axon hillock. The axon hillock is a specialized part of the cell body or the soma of a neuron that connects to the axon. The axon hillock is the last site in the soma where the membrane potential propagated from the synapse inputs are summated before being transmitted to the axon. So as I said before, we use oscilloscopes to measure the amount of electrical charge So as I said, we use an oscilloscope to determine the amount of charge. If a neuron binds and the receptor opens up and sodium enters the cell, this causes a bump. You can see the bump right here during the depolarization. The ESPS is a postsynaptic potential that makes the neuron more likely to fire the action potential. So this makes the action potential more likely to fire. The depolarization of the cell is caused by the entering of sodium. When there are a multitude of neurotransmitter molecules, the ESPSs add up and create a summation effect. This is the summation effect, and it makes it more positive. This is called the temporal summation process, and this initiates the action potential. The receptors that cause this threshold of excitation are on the axon hillock. The axon hillock is right here. This right here is the axon. The axon hillock collects all of the electrical potentials. It causes the opening of the voltage-gated channels. It looks like a receptor, but it doesn't have a binding site. Once the negative 65 threshold is released, it causes an excitation of the action potential at the axon hillock. The action potential is generated from a resting state because of summation of many ESPSs reaching the threshold of excitation. This causes a massive increase of sodium inside of the cell. The threshold changes from negative 65 to negative 55, and depolarization occurs. Sodium is now at equilibrium, and potassium gates open. The cell is positive, and the concentration of potassium is higher inside the positive cell, and the positive cells repel each other, which causes potassium to now exit the cell. So because of potassium exiting the cell in attempt to maintain homeostasis, potassium is attempting to maintain homeostasis. The equilibrium point is at negative 75 millivolts, and this causes the cell to come back at rest. These are a few more, the last key terms that you should be familiar with for the last part of my neuron story. Hyperpolarization is a change in the cell's membrane potential that makes it more negative. It inhibits action potentials by increasing the stimulus required to move the membrane potential to the action potential threshold. Depolarization refers to the sudden change within a cell which the cell undergoes a dramatic electrical change. And lastly, exocytosis is a process by which the contents of a cell vacuole are released to the exterior through fusion of the vacuole membrane within the cell membrane. These are the nodes on the axon. Please remember what I said about the train. Just imagine that the neurons are traveling in the train, and then they keep making stops and stops at each station. People are getting off, changing the dynamic, making it negative and positive. And then eventually it stops and everyone disperses. So lastly, in each node, you have a potassium and sodium gated channels. The action potential moves down the axon shaft from node to node, like from station to station. And finally, the action potential reaches the buttons. These are the terminal buttons. So after the action potential moves down the axon shaft from node to node and it finally reaches the terminal button, it interacts with calcium. And the vesicles bind to the inside of the presynaptic membrane, and it opens during exotosis. Remember, exotosis is the process when the contents of the cell vacuole are released into the exterior through fusion, and the molecule of the neurotransmitters are spilled out into the synapse between cell B and C. And this is the space. So again, just remember, this cell is attempting to maintain homeostasis. So that's the end of my story, but I'm going to go through it one more time just in case you guys missed something. So if this is a 3-cell network, there would be a cell A, cell B, and cell C at the end of the terminal buttons. A neurotransmitter is released from cell A. It attached to the dendrites. It goes down the dendrites to the cell body. It goes down the axon through the cell membrane. Now remember, once it goes to the cell membrane, on the axon, there are all these nodes, which are the stops on the train. And the nodes have potassium and sodium gated ion channels. So as the action potential moves down the nodes, it finally reaches the terminal buttons where it interacts with calcium. And it binds to the site of the presynaptic membrane. And then they open during excitosis, which causes the molecules of the neurotransmitters to be spilled out of the synapse between cell B, and cell C, which is not here, of course. Thank you so much for watching my video. I hope that I can help you better understand the concept of the neuron story. Thank you.